Hey, today's lesson is on the normal distribution. The normal distribution is a symmetric bell-shaped distribution with a single peak. Its peak corresponds to the mean, median, and mode of the distribution. Its variation is characterized by the standard deviation of the distribution. This figure shows two distributions. A famous data set of the chest sizes of 5,738 Scottish militiamen collected in about 1846, and the distribution of population densities of the 50 states is either a normal distribution. Well, if we look at the second one, this one is definitely not normal because we want it to do this deal. And so the population of the United States would not be normal here. So we'll say not normal. A few of the states have a great amount of population density, but the rest of them don't. The first one is normal, though. It does look like a nice single-peaked symmetric bell curve. No, it's not perfect, of course, but it is pretty close. So we will say that the chest sizes of these Scottish militiamen would be a normal distribution. A data set satisfying the following criteria is likely to have nearly normal distribution. Most data values are clustered near the mean, given the distribution of well-defined single peak. Data values are spread evenly about the mean, making the distribution symmetric. Larger deviations from the mean are increasingly rare, producing the tapering tails. And individual data values result from a combination of many different factors. Which of the following variables would you expect to have a normal or nearly normal distribution? Scores on a very easy test. So if the test is easy, most scores will be good, right? And maybe a few, if they didn't even do it, will not be good. So this distribution is most likely to look something like this. And so we would say that this one is not normal. It's skewed. Shoe sizes of a random sample of adult women. Well, we expect shoe sizes, I think average is about a 7. So we expect most women to have a shoe size of around that. And then there might be, I'm not going to even worry about halves. There are probably several 8s and several 6s. I'm just guessing here. But 9s are a little more rare. 10s are even more rare, and so forth. 5s are very rare. That's me, or smaller. So I'm stuck down there. Difficult time finding shoes. But yes, we would expect this sample to be normal. Example 3 says vending machines can be adjusted to reject coins above and below certain weights. The weights of the legal U.S. quarters are normally distributed with a mean of 5.67 grams and a standard deviation of 0.07 of a gram. If a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53, what percentage of legal quarters will be rejected? Well, 5.81 grams is how many grams away from the mean, or how many standard deviations from the mean. Let's see. 5.81 minus our mean is 0.14. And the standard deviation was 0.07. So it's 2 standard deviations above the mean. And then 5.53, if we take our mean and subtract 5.53, we also get 0.14. So it's 2 standard deviations below the mean. So if the machine accepts quarters, we've looked at this before, that are from 2 standard deviations below, that's not a very good picture, to 2 above, then by the 68, 95, 99.7 rule, 95% of quarters will be accepted, and 5% will be rejected. So the 68, 95, 99.7 rule is what we just talked about in that previous example for a second. And it looks like this. If you've got a normal distribution, then we expect 68% of the data to lie between 1 standard deviation below the mean and 1 standard deviation above the mean. We expect 95% of the data to lie between 2 standard deviations of the mean. And then 99.7, almost all of the data, will lie between 3 standard deviations of the mean. So for example 4, it says, assume that a set of test scores is normally distributed with a mean of 85 and a standard deviation of 5. Use the 68, 95, 99.7 rule to find the following quantities. So the first thing we need to do is label this graph I provided us with our scores. The mean is 85, so I'm going to put that right there. And then the standard deviation is 5. So what we do is 1 standard deviation above will be 85 plus 5, 90. Add another 5 for 2 standard deviations, and another 5 for 3 standard deviations. And then we subtract the opposite way. So 1 standard deviation below the mean will be 85 minus 5, or 80. Then subtract another 5 and another 5. So it asks us, find the percentage of scores greater than 85. So here's 85. And if I shade, and I don't have a highlighter in this application, I wish I did. But if I shade everything to the right there, then we can see that it's actually just half. So 50% of the scores will be greater than 85. For part B, we want to find the percentage of scores that are greater than 90. So here's 90. And so we want the scores that are only to the right of 90. Okay? So let's see. We've got to figure this out. In order to figure this out, we can use the fact that from here to here is 68%, right? So if we subtract 68 from 100, we get 32. So to the right of here and to the left would be 32% of the population. But we want just to the right. So divide it by 2. 16% of the population has scores greater than 90. And C, find the percentage of scores between 75 and 90. So here's 75, here's 90. This one's a little bit more complicated. Okay, that's good enough. So, again, we know that from here to here is 68%. Okay? And we know from here to here is 95%. So if we take 95 and subtract 68, then we would get just there and just there. So let's see what that is. 27. So both here and here is 27%. If we divide that by 2, we get that each of these is 13.5%. So now all we need to do is take the 68 here and the 13.5 there and add them together. 81.5% of the scores are between 75 and 90. The number of standard deviations that a data value lies above or below the mean is called the standard score or z-score. So we won't always lie exactly 1, 2, or 3 standard deviations above or below the mean. It could be 1.5 or negative 2.37, okay? So we can't always rely on that nice 68, 95, 99.7 rule. We have to use something called a z-score. And a z-score is found by taking whatever data value you're given, subtracting the mean, and dividing by the standard deviation. So example 5 says, the Stanford-Binet IQ test is scaled so that scores are normally distributed with a mean of 100 and a standard deviation of 16. Find the standard scores for IQ scores of 85, 100, and 125. So all we need to do is plug into that formula our data value, which in the first case is 85, minus the mean, divided by the standard deviation. We get negative 0.94. Then the second one, for 100, it'll be our data value of 100 minus the mean, divided by the standard deviation. That's just going to get us 0. And for 125 minus the mean, divided by the standard deviation, 1.56. The nth percentile of a data set is the smallest value in the set with the property that n% of the data are less than or equal to it. Data value that lies between 2 percentiles is said to lie in the lower percentile. We'll come back to that. So actually, let's talk about this. So if you've got your z-score, then you can use this table to help you find the percentile. So looking back at example 5, the z-score was negative 0.94. And so that's, approximately, there's negative 0.95, so pretty close. So the percentile would be 17.11%. Now, what this means is important, okay? This does not mean that you scored you got 17.11% of the questions correct or something like that. No. This means that if your IQ is 85, then you scored better than 17.11% of the population. If the z-score was 0, it's pretty straightforward. You scored better than half of the population. If the z-score was 1.56, let's look over here. We've got 1.5 or 1.6. Let's look closer to 1.6. So 94.52. If your IQ is 125, then you scored better than 94.5% of the population. You're one of the smartest people on earth. Example 6 says cholesterol levels in men 18 to 24 years of age are normally distributed with a mean of 178 and a standard deviation of 41. In what percentile is a 20-year-old man with a cholesterol level of 190? So we find the z-score first, taking 190 minus our mean divided by the standard deviation. We get about 0.29. So we go back here, and I think there's a 0.3 on here. Yep. 61.79. So about the 62nd percentile. So that means, again, that his cholesterol level is better than 62% of the population. What cholesterol level corresponds to the 90th percentile, the level at which treatment might be necessary? And actually, since a bigger number is worse in this case, then we'd say his cholesterol is worse than 62% of the population. Sorry about that. Okay, so 90th percentile, if we look back at our table, and the closest thing to 90th percentile is 90.32. So that's a z-score of 1.3. So it says what data value, what level would correspond to that. We're going to plug into our formula, except we're plugging in 1.3 for z, and we need to solve for x, where the standard deviation, or the mean, was 178, and the standard deviation was 41. So multiply both sides by 41. And we have x minus 178 is 53.3. Add 178 to both sides. and we have 231.3. So if a man between the ages of 18 to 24 has a cholesterol level of 231, then he may need treatment.